The purpose of this challenge was to remind you how far you can get just using your high school physics. So guess like a physicist was actually an overstatement. You don't have to be one to make physics very useful for what you're doing. All right, let's get to it. You kind of know what's coming, right? I want to calculate the potential energy in the system, and I'm going to somehow extract what I need from what I see here on the screen. This is all super crude, but the simplest way I could think of was to overlay a piece of paper and to trace the shapes. First thing is the man. With the help of that vest, I can come up with a good size approximation. Let's just hope that the company didn't hire a tiny person or some kind of a giant to be the operator. I am running on the assumption that we're looking at an average human being, meaning this slightly overweight gentleman is 1 meter and 80 centimeters tall. Next, the points of rotation for the arm. I'm guessing there's one down here, there's one up there, and there's a third one for the bucket. That is probably not going to be too relevant for this calculation, but it's there. And I'm making a stick figure-like drawing that shows these things, and that's essentially all I need. So next I'm going to take my stick drawing here and I'm going to have to add some paper at the bottom since I actually want to dig a hole. I'm using sticky notes to first make myself a man-size measure representing 1 meter and 80 and a few more stickies for the excavator's arm and the bucket. Now I have an arm that can actually reach down into that hole and I can use that to get a good guess on how deep this machine might be able to reach. It looks like we are at just a bit less than 3 average man sizes deep. It sounds a bit optimistic, let's just go with that. What are we going to do with the dirt? We are going to load it onto a truck and haul it away. And from what I sketched here, it seems like my truck is just a bit more than one average man high. So roughly our total height here seems to be 4 man heights, which, if my math is right, should be like 7 meters and 20 centimeters. But we're guessing here, and I really don't need stuff behind the decimal point. Therefore, let's declare it nice and round, 8 meters. So far, so good. Now, what's the mass here? Let's have a look at this bucket. I'm placing it next to my man, and I'm counting out the teeth that it must have at its lower edge. And doing that, I could guess that this is a meter high, is that right? But it's all round and stuff, and these things are usually much narrower than they are tall. And to make it simple, I declare this bucket roughly equivalent to a cube with a side length of 60 centimeters. Okay? Doing the math, it seems my bucket might have a volume of like 200 liters. And if my dirt is as heavy as water, these 200 liters are 200 kilos. So let's just roll with that and not think about rocks and other heavy objects and whatever might be in the bucket. Keep it simple. So mass times height times Earth's gravity, which I will call 10 in the general spirit of simplicity, gives us a 16,000 joule energy that it takes to lift one bucket of stuff out of this hole. Joule is just another way of saying watt seconds, which are just another way of saying kilowatt hours, which is what you see, for example, on your energy bill from BC Hydro every month. But since we got an excavator and we are using it to dig all day, this energy is needed every single time I'm lifting a bucket of stuff out of that hole. Round trip for the bucket in this precision simulation appears to take 13 seconds, which I naturally don't like, and I declare it to be 10 seconds instead, because 10 is just such a nice number. And the operator is really skilled and much faster than I am. So if this happens every 10 seconds, it means it will happen 2,880 times a day in an 8-hour shift. There we go. All these buckets of stuff taken out of this hole represent a total of 13 kilowatt hours of potential energy. BC Hydro would charge you 85 cents for that. And now comes the interesting part. What's in a liter of diesel? How many kilowatt hours? It turns out it's about 10.5, which is wonderful because it can be rounded to 10. Or one can write down 1 liter again on a piece of paper for no good reason. Anyways, so how good is this number actually? Well, there are a few problems here. This entire system to convert diesel into work to dig a hole has efficiency problems. First, there is the engine, which loses something, and not knowing what it is, I'll just call it 50%. Good guess if I have no idea. Actually, I do know it's 50 is a really good number. It's not quite that good. Engines lose more than that, but let's just go with it. As a result, to get the energy that I need for my work, I need to burn 2 liters. But there's more to this machine. There's the entire mechanism and the hydraulics and all. And again, I have no idea what the efficiency here would be, and I simply call it 50% again. By now, I have to fill in 4 liters of diesel for every day of digging. Or do I? Actually, it's even worse. The machine itself has parts that get lifted every time I'm digging dirt, and that just costs more energy. How much? Let's guess. Let's just say this machine is not super big, maybe it's the size of a big SUV, and if a big fat SUV is 3 tons, maybe this thing is 4 tons. But the arm is what's interesting. That's the tool that I'm lifting for every batch of material moved out of the hole. How heavy is the arm? I don't know. Maybe a quarter of the machine's overall weight? It can't be much more, because if it was, the machine could tip over and fall into the hole when the arm reaches far out. So let's just say the arm is 1 ton, 1/4 of the total weight. Meaning, if I need 4 liters to lift the stuff, I will need another 20 liters on top of that to just lift my tool, the arm. Wow, 24 liters total for just 1 day of digging. Can that be right? Let's have a look. After a bit of Googling, I find that this machine might be a Case 580N loader. And on page 2, the manual says it has a tank of 132 liters. What it doesn't say is how long the machine is expected to operate with that. So there you have it. This guess might be in the right ballpark. Think about that. This is what you can extract from just looking at something if you put your mind to it. And that's not even all. Just think about it. Once you know the energy, you can go from there to get other specs that might be of interest. Like, for example, what power does it take to do this work in a certain amount of time? Or torque. What kind of torque does the arm of the machine have to deal with when it's extended out all the way? Imagine somebody told you to design an electric excavator that uses motors to move the arm and do the digging. You need to calculate torque, you need to calculate power, and I leave you with that. That was it. See you for the next one.